So I got another object that we're going to find the volume of. The question was asked earlier. It's like, are we going to do volumes of like other things? Yes. Okay. And what we're going to do is we are going to place objects on top of a region. Like squares, like semicircles. So that we have a shape that has a flat bottom. But then we will take an object and place it on, a base of the region, like perpendicular to the x-axis. A square would come out of that, and put a bunch of squares, and you create that shape, that three-dimensional shape. Or like, you could go perpendicular to the y-axis, and this is how they're going to ask you to do it. It's like, put a square perpendicular to the y-axis on the region, create a shape. What is the volume of that shape? Now, maybe that doesn't make sense to you, but this person put together this sweet visualization. Props to this guy. He's a teacher in New York. Okay, so we have this region. It's y equals x squared and y equals root x. Okay, and we have, a distance between, refresh. Cool. And you're going to be told, hey, place a square perpendicular to the x-axis on this region. Okay? Now, I just placed a square, but it's like, oh, nothing happened. But no, what happened is you took a square, you placed it on this purple line, and boom, now we have a square right there. Cool. All right. Now, the square size could change. If we are like right here, you place a square right there, it's a small square. If you go right here, we got a bigger square. Okay? But what we're going to do is place squares everywhere. So this object has squares placed on the region everywhere. And this is the three-dimensional object created. Okay, pretty cool. It's got a flat bottom, but boom, that's what it is. Now, the question is, how are we going to calculate the volume of that object? Well, we'll use our friend the sum. And if I know the volume of this one square, we can like sum up the volume of all of the squares. Cool? But the question becomes like, what's the volume of the square? Well, here's another visual example. This is the square that we're talking about. Okay? Goes right here. Okay? That's the square. Piece of paper. Does a piece of paper have volume? Sure, or else I wouldn't be able to hold it. It's got to be three-dimensional or I can't grab it. Put your phone away. Is that a phone? That's not a phone. All right. What's the volume of this square, of this piece of paper that's coming out?
The width times the very thin.
Yeah, it's like a three-dimensional thing, so it's got three dimensions, a length, a width, and then like a height, right? Well, it's really just a side length squared because it's a square, okay? But let's just go with L, W, and H. L times W gives you your area of your square, okay? Then times the height, the small x distance. So the volume is just the area of the square times the skinny height. Now, if I oriented my square this way, it'd still be the area of the square, but now the height is a very small y distance. That's it. It's actually a lot easier than spinning things because all we're going to do is sum up volume formulas of our individual objects. Now, like, we might not always have squares. I'm sorry, let's go back. You could have other objects like circles, semicircles. Okay, what would be the formula for the volume of a semicircle cut out of paper? Yeah, like the area of the semicircle times the very skinny width. 3 dimensions got a volume. Okay? So we could have triangles, we could have semicircles, we could have rectangles, and we will just be able to sum up the volume of our individual objects.
So would that be like a semi-cylinder kind of because it has that width, that height to it?
Yes.
Okay.
Good. But the volume of your individual objects, since they're all like skinny objects, will just be like the area of like the face of your object times the skinny height. But the skinny height is either a dx or dy depending on its orientation. Okay? Now, what's that look like in terms of like a problem? Say this is like f of x equals x plus 4. Say this is g of x equals sine x plus 3. Okay, these are two y equals equations. And I say, hey, put perpendicular to the x-axis squared. So this is a line perpendicular to the x-axis. This is the first thing that's important. You got to understand how your objects are being placed. They're placed perpendicular to the x-axis, so boom. Then we will have squares popping out of our region. There's that square popping out. The square size is going to change, just like we saw on that demonstration. Well, how are we going to find the volume? We will sum up our areas of our squares times their very skinny height. Well, the very skinny height in this case is a very small x distance. Like that is a small x distance. That's the height. Okay, so I just need some sort of area of my square. Well, I know the area formula of a square is a side length squared. This would be my side length. So I will sum up my side length squared to get the areas times the skinny height to give them a volume. My side length is a vertical distance. It's a y equals top minus a y equals bottom. I sum up vertical things from left to right. It makes sense. You use your pencil to kind of help you, and you go 0 to 5. Plug that into your calculator. You're done. Okay? Let's skip the semicircle. Let's go to rectangle. Height is 3 times the length. All right, well, all I need to do, sum up, the area of my rectangle times the skinny height. In this case, the height is still dx because it's a vertical. So like small width, that height, dx distance, small x distance. And then we're like, okay, well, what's the area of a rectangle? Yeah, like a base times the height, or length times the height. The problem is it's like, what's the length? What's the height? Well, you know what? Instead of doing L times H, we realize that our rectangles are very specific. The height is 3 times the length. So H is 3 times the length. Well, why don't we just change our area formula to say we got L times 3L, and we can either write like my length times 3 times my length, or change this to 3L squared. And then instead of worrying about like base times height, we can say, oh, for this rectangle, whose height is 3 times the length, we have 3L squared. What is the length? Well, it's this length. Again, it's the y equals top minus the y equals bottom. What did I say? X plus 4. Y equals x plus 4 minus y equals sine x plus 3. Summing them up from 0 to 5. Boom. Now, write isosceles triangles. What's the area formula of a triangle? 1/2 base times height? Well, it's isosceles. So the base and the height are the same. And we're always going to put our isosceles triangles down so that this length and this length are the same, and the hypotenuse kind of connects them. So, since the base and the height are the same, 1/2 my base length squared. You want to find the volume of this object where it's right isosceles triangles, sum up 1/2 base length squared. Top minus bottom gives me my base length. It's really the same stuff as what we've been doing, just looks a little different. But now let's go back because the semicircle is a little bit tricky. Okay, so it's like, we'll skip this whole area of a semicircle and just say the area of a semicircle is 1/2 pi r squared. Again, it's perpendicular to the x-axis, so it's 0 to 5. What's r? Hold the phone. If we take a semicircle and place it on my region, what do we realize? This length is the diameter. We want the radius, which is half of my diameter. That length is going to be my diameter. I want my radius, which is half of my diameter. So that's one little trick. All the other ones, it's always top minus bottom. For this guy, top minus bottom divided by 2 is usually easier to type in your calculator. But even that's kind of tricky to type into your calculator, especially if you don't have alpha F1. So I'm actually going to introduce to you a different formula for a semicircle, which you may use or choose not to use. The area of a semicircle is 1/2 pi r squared. I'm going to write that as immediately as d over 2 squared. Well, I can simplify this and do 1/2 pi d squared over 4, which is the same as 1/8 pi d squared. This is an area formula based on a diameter. You may choose to type this into your calculator and you'll get the right answer. But you will get the exact same answer if you type in 0 to 5 of 1/8 pi top minus bottom squared. Okay? So, just an interesting thing that could be done if you choose to do it. If we put things perpendicular to the y-axis, something perpendicular to the y-axis looks like this. Perpendicular y-axis looks like this. We're still going to be summing up area formulas, but my piece of paper is now rotated. It's on its side. It's almost like my region looks like this now. Not a great example, but just to show you, like the square is based on our base length. The base length is an x distance. Now, like the width of my piece of paper is a small y distance. So, side length squared, but times a small y distance to give it 3 dimensions. X equals right minus x equals left for my base length. I didn't give you equations, so don't worry about it. I mean, it would be like k of y minus h of y. But I'll just go with x equals right minus x equals left. And then just like we're used to, when we sum up horizontal things, we like to go from a bottom to a top, 1 to 6. Okay? I'll see, this is it. Nothing crazy. Do a couple examples, and then, like, you're ready to go. Well, I told you this is like just the same stuff as what we've been doing, just going to look different. All right. We have a familiar region, y equals x squared, y equals 4. I would like you to find the volume of the solid whose known cross sections perpendicular to the x-axis and y-axis, we're going to do both, are squares, whose base is bounded by y equals x squared, y equals 4. All of these words are somewhat confusing to a lot of students. Okay? But what you need to focus on is perpendicular to the, let's start with x-axis. One thing you need to focus on. Second thing you need to focus on, and a lot of people kind of skip over this, is the object, squares. I'll do perpendicular to the x-axis in red. So here's something perpendicular to the x-axis. Boom. Here's something else perpendicular to the x-axis. Boom. I'm placing a square on top of that. To get the volume, I need to sum up all of these squares. Okay? Well, I will sum up the square's volume. The area of a square is a side length squared. So I'll take my side length squared times their skinny height. In this case, it's a skinny x distance. I like to sum vertical things up from left to right. It makes sense. I got to find this intersection. It's obviously a 2. And my side lengths of my squares are a top minus a bottom. 4 minus x squared. Done. Easy. Okay. Well, what if it's perpendicular to the y-axis? I'll do perpendicular to the y-axis in purple. Here's perpendicular to the y-axis. Putting squares on this. Putting squares on all of these cross sections. Well, I'll sum up side length squared times their height to give it 3 dimensions so that it's a piece of paper. Very skinny, doesn't have much volume, but it has volume. Okay, and this is now an x distance. X distance, x equals root y minus x equals 0. Summing them up from 0 to 4. Now, if we were to do semicircle, you could either do 1/2 pi d divided by 2 squared. Boom, you have a semicircle. If you have isosceles right triangles, you have 1/2 base squared. You know, it's like that's all it is. Do the one. You can choose to do 1/8 pi d squared. You can do 1/2 pi d divided by 2 squared. That's really it, though. This is the lesson. You should be able to do the homework based off of what we just did. Yeah.